Okay, let's put together everything we've learned so far and add in a little bit of logic to find all zeros of the following polynomial. F of x is equal to x to the fifth minus 2x to the fourth minus 3x cubed plus 2x squared minus 5x plus 12. Alright, so one of the things that we know is the rational zeros theorem. So if there are rational zeros, they're going to be some combination of p's and q's, right? So the p's, the possible p's, remember, are the factors of this coefficient here. So those would be 1, 2, 3, 4, 6, and 12. Okay, those are all the factors of 12. And then q is the factors of the leading coefficient. So in this case, it's just 1. So that means P over Q, the list of all the possible rational zeros for this function are just the P's, right? Because everything in the P would be divided by 1. And so we could just write those out again. We have possibly 1, 2, 3, 4, 6, and 12. Okay, but there's a way that we can go about kind of narrowing down our search. And one of the ways, there's several ways. One of the ways is Descartes' rule of signs, right? So watch the previous video if you don't know what Descartes' rule of signs is, but it's a pretty neat way that we can determine the possible combinations of zeros of a polynomial. And in the end, what we're going to do is we're going to generate this little table where we have positive real zeros, negative real zeros, and then non-real zeros. And we're going to kind of list the possibilities here. So first of all, f of x, right? F of x is what's given to us. It's x to the fifth minus 2x to the fourth minus 3x cubed plus 2x squared minus 5x plus 12. We look at the sign changes here. This is f of positive x, so we're going to count the number of sign changes. There's 1, no, yes, 2, yes, 3, yes, 4. So that means for f of positive x, that means that when we count 4 sign changes, that means there are 4 or 2 or 0 positive real zeros. Okay, so we have the possibility of 4, 2, or 0 positive real zeros. Now we have to look at f of negative x. Okay, f of negative x is going to equal, the odd ones are going to change signs, and the odds change signs in evens don't. So this will be negative x to the fifth minus 2x to the fourth plus 3x cubed plus 2x squared plus 5x plus 12. Okay, so count the sign changes here. We have negative, negative, no, negative, positive, yes, positive, positive, no, positive, 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 no. So there's only one. So that means this is really very useful, actually. There is only one negative real zero. So it doesn't really mean there is only one, but it means that the graph of this thing crosses the x-axis on the negative side once. So that means for all of these options, we could have 1, 1, or 1. And that means we would have 0 complex, or 0 non-real zeros for the first option because they have to add up to 5. That's what the fundamental theorem of algebra says. For this scenario here, we'd have to have 2. And for this scenario here, we'd have to have 4. So there are only 4 possible combinations. Three possible combinations of zeros for this, and they have to come, if there's going to be a rational number, it has to come off of that list that we came up with. Okay, so here's what we got, and to illustrate what I'm going to talk about next, I'm going to draw the graph of this first possibility from Descartes' rule of signs in green. I'm going to draw the second possibility in red, and the third possibility in blue. So something I know, because this is a fifth degree polynomial and the leading coefficient is positive, is that it's going to follow the behavior where it starts in the bottom left and goes to the top right. We'll discuss more about how to talk about that situation later. But I know that all polynomials of odd degree that have a positive leading coefficient look something like that. And the higher degree, the more complicated they look. But you can think of just y equals x as the most simple example of that. So anyway, going back to this options, right? The green option, we could have our 1 negative 0 and then 4 positive real zeros. So it could do something like that. The red option, we could have our 1 negative 0 and then our 2 positive, and then it does something like that. Okay, and then the third option, the blue option, we could have our one negative, and then that's it. It doesn't go back across the x-axis ever again. And this tells us actually a couple of very important things. First of all, since I know there's a negative, I know that this if I evaluated the function at 0, it would have to be positive. And I know that because it has to cross the x-axis on the negative side, and then it has to cross the y-axis in order to get to the negative side of the x-axis. So no matter what happens on this side, it had to cross the y-axis on the positive side. And we can verify that, right? If I wanted to know f of 0, well, I just plug in 0 for all of these things, for all x everywhere, and I have 12 left. And so f of 0 is 12. Importantly, it's positive. It doesn't matter that it's 12. It matters that it's positive. And why it matters that it's positive is because of something called the intermediate value theorem. Let me explain what that is. All right, let's assume for right now that the red graph is the right graph. Okay, so let's say that this graph does something like this. Okay, now I already found that the f of 0 is positive. If I could find a value for x, where if I plugged in something over here, let's say, oh, I don't know what it is, if I plugged in negative x over here, right, and I got a negative value out, what this means, because I'm working with polynomials, which are called continuous, is that there must be at least one, and we know for this case there is one because I already did Descartes rule of signs, but there must be at least one negative, or there must be at least one 0, meaning it has to cross the x-axis somewhere in this area. It has to. It goes from negative to positive. The only way that can happen is if it crosses the x-axis. And so we can use this to our advantage. Now, I previously said that when you talk about the rational zeros theorem, that you start with the lowest possible values, right? You start with the lowest whole numbers because it's just easier to evaluate those. And so I'm going to depart from that just to illustrate how this works. If I wanted to evaluate f of negative 3, so I'm choosing negative 3, that's the same thing as if I do synthetic division with negative 3, right? So let's do that real quick. Negative 3, we have 1, negative 2, negative 3, 2, negative 10, and 12. And then those are the coefficients. And then so we do synthetic division here, and we will get 1, negative 3, negative 5. We get, that's 15. Then we get 12, negative 36, negative 34, 90, 102, right? Positive 102, and that's 92. Then negative 3 times 92 is negative 276. 12 minus 276 is negative 264. So what that tells us in this case is that, like, if I had plugged in negative 3, I would get a big negative value out. And I already know when I plugged in 0, I had a positive value out. So the only possible place that I should be looking for a negative real 0 is between negative 3 and 0. It would be a waste of time to look for like negative numbers that are less than negative 3. So basically, if I go back and look at my list, if I'm evaluating these for the negatives, I just shouldn't look at the 4, the 6, or the 12. There's no way. And that will tend to be the case for polynomials, is that the zeros tend to be closer to the y-axis. And so two different ways to think of this. Now let's go ahead and try another number. So again, the only ones we should be trying are negative 1 and negative 2, because we already ruled out negative 3, and it can't be anything less than negative 3, like to the left of negative 3 on the number line. So let's try negative 2, f of negative 2, and we can do this by synthetically dividing also. It's the same thing. We could also just plug in negative 2 for x, but let's just do synthetic division here. So the coefficients again are 1, negative 2, negative 3, 2, negative 10, and 12. Okay, and we're going to plug these in. So what we get is we'll do 1, negative 2, negative 4, 8, 5, negative 10, negative 8, 16, 6, negative 12, 0. Okay, so cool. So now our condensed polynomial here, right, is x. We started with fifth, so now it's x to the fourth minus 4x to the third plus 5x squared minus 8x plus 6. Okay, so So cool, I found -2 as my -0, and that was the only -0. The rest of them are positive, so I'm not going to look at any other negative numbers. So I'm only going to be looking at positive numbers from this list here. And so let's just go back to our other way where we start by evaluating like the lowest whole number, right? The lowest whole number, so 1, right? If we plug in 1 and we do synthetic division, actually, since we know that this is a condensed polynomial, now we can use these coefficients, the 1, the -4, the 5, the -8, and the 6 when we do more synthetic division. Because if there's a factor of our original polynomial, and this is a factor of the original polynomial, then any other factors we get have to be factors of this new condensed polynomial. So let's try 1, right? If we try 1, we'll have 1, and then the coefficients are 1, -4, 5, -8, and 6. Let's go. So 1, 1, -3, -3, 2, 2, -6, -6. Okay, cool. Boom. 1 is a 0 also, right? 1 is a 0. That means x minus 1 was a factor. So we have this new condensed polynomial would be x cubed minus 3x squared plus 2x minus 6. All right, we tried 1 and it worked. Let's try 2. Okay, so we're going to do 2. All right, so we've got 2. We've got, then we'll use these coefficients now. Okay, so 1, -3, 2, -6. And we're trying 2 here. So we go 1, 2 times 1 is 2, -1, -2, 0, -2, -2, and so this doesn't work, right? Okay, so this negative obviously doesn't work, but we do know something interesting, that it's -6 here. Okay, so we found one positive 0 here. Okay, which means that it's not this one, because if we found one positive 0, there must be at least one more. And we found also that when we plugged in 2, so let's say like this was -1, right? Or sorry, positive 1. When we plugged in 2, we got a negative number out. So let's try the next number, and hopefully we'll find a 0 there. So let's try 3. Okay, so 3, and we're going to use those same coefficients again. All right, now we'll do, so we got 1, 3, 0, 0, 0, 2, 6, 2, 0, 2, 6, 0. Oh, cool, 0. Okay, so what we end up with then is this new polynomial of x squared plus 2. And it doesn't, you don't have, this is a quadratic, and you could tell right away that this does not factor. And so what does this mean? Well, if we were to write out our new polynomial, and remember we're asked to find a 0, so we're not quite done yet, then we've got this going on. We have x. We found that 2 was a 0, so x plus 2. We found that, so the correct zeros were 1, 2, and 3. 1, -2, and 3, right? So those would correspond to x plus 2, x minus 1, x minus 3, and then this last thing, x squared plus 2. So that's the factored polynomial right there, but we were asked to find the zeros. Okay, so the last step here, right? We found these zeros, and remember our factored polynomial was f of x is equal to x plus 2, x minus 1, x minus 3, and then x squared plus 2. So if we want to find the zeros, well, zero product property. So we'll have x equals -2 from this one, 1 from this one, 3 from this one, which is what we found those, right? And then x squared plus 2. So what are the zeros for x squared plus 2? Well, x squared plus 2 equals 0, x squared equals -2. If we square root both sides, right, we'll get that the absolute value of x is equal to the square root of -2, or x is equal to plus or minus the square root of -2, and then we can write that as x equals plus or minus I times the square root of 2. And so that's what we have right there. Those are the other two zeros. So all 4 of the zeros then are -2, 1, 3, and plus or minus the square root of 2 times I, or plus or minus I root 2. So that means that this function, the graph of this, was something along the lines of the red one we drew on the previous slide. So it had a 1 0 or 1 negative 0 that was at negative 2, and then it had a 0 at 1, and then a 0 at 3, and did something like that. Now this is a very simplified graph. There's some weird things happening here because of the plus or minus square root of 2i. But it's interesting that we can find all this information about this polynomial without having known really anything about it in the first place. And so that's kind of from A to B, or A to Z, I guess, when it comes to finding the zeros of a polynomial.